In the previous session, we have been discussing about the optimum receiver for digitally modulated signals over an additive wide Gaussian noise channel. We will continue that discussion further and look into some other aspects. And if you recall, in the last session, we discussed about the correlation receiver, and we saw the statistical properties of the demodulated signal, demodulated using the correlation receiver. Okay, today we are going to see another method of demodulation, and we will also discuss why we need another method, what are the challenges or difficulties or disadvantages of the correlation receiver that it necessitates another method, and then we will also see what are the advantages of this new method of demodulation that we are going to discuss today. Okay, so before we dive into the topic, let us also recall what is the situation we are dealing with. The situation we are dealing with is an AWGN channel, an additive wide Gaussian noise channel, where we have the received signal to be equal to the sum of the transmitted signal and the noise signal. Okay, so the transmitted signal is any one of possible m signals. So we have a set of m possible signals. Each of those signals denotes a particular symbol, and the transmitter would be transmitting one of those signals or waveforms depending on which symbol it wants to transmit. So we have m possible symbols, and therefore m possible signal waveforms which the transmitter would transmit, and on the channel additive white Gaussian noise gets added. So the channel adds white Gaussian noise. And what do we mean by white Gaussian noise? By white we mean that its power spectral density is flat, and that means it has a flat power spectral density of n0/2 for all frequency values, and the statistical distribution of the noise samples is a Gaussian distribution with a mean value of 0. So it is 0 mean Gaussian noise, and it has a flat power spectral densities, therefore it is white Gaussian noise. Okay, so for the power spectral density being flat, the autocorrelation function is an impulse function. That means the correlation between the samples is 0 except when the shift between them is 0. So there is a correlation only if the samples are perfectly aligned without any shifts. So the autocorrelation function becomes n0/2 delta of tau, and tau is the shift or delay, and delta of tau is non-zero only for tau equal to 0. So we have basically what we are saying is that the noise samples are uncorrelated. And then we also can deduce the average noise power to be from the autocorrelation function by evaluating the autocorrelation function at tau equal to 0. So at tau equal to 0, we get the noise power to be n0/2, and for the 0 mean random process, for the Gaussian process, which is also ergodic, the noise power is given by its variance when the mean is 0, right? And since we are dealing with 0 mean Gaussian noise, so the variance sigma square denotes the average noise power. And then we also have the vector representation of the transmitted signal. So we have the transmitted waveform Sm of t, and each of those waveforms can be represented in the signal space as a vector of length n. So we have this vector Sm which contains n elements, so 1, 2 up to n elements. So that means it's a vector of length n, or in other words, the signal is represented, or the waveform is represented as a vector or point in an n-dimensional signal space, where the axis of the n-dimensional space are represented by n orthonormal basis functions. So we call these basis functions as phi j of t for j1 to n. So that means we have n basis functions which we denote as phi 1 of t, phi 2 of t up to phi n of t. Now, what do the elements of the vector represent? What does each of these elements represent? These are the projections of the signal Sm of t onto each of these basis functions. So Sm1 is the projection of the signal Sm of t onto the basis phi1 of t. Sm2 is a projection of the signal onto the basis phi2 of t, and so on. Okay, so the projections give us the elements of the vectors, the projection of the signal onto each of the basis functions. Those are the elements of our vector that represent the signal in the signal space. Okay, so that's just a quick review of the things that we have been discussing so far. Now, in the previous lecture, we discussed about the correlation receiver, and we talked about the functionality of the receiver being divided into two parts. Okay, so the receiver functionality is divided into two parts. The first part is called as the demodulation part, performed by the demodulator, and the second part is the detector part, performed by the detector. So the demodulator's job is to convert the signal waveform into its vector representation. So from Sm of t, it has to convert it to the vector form Sm. In the case of the received signal, it has to take a received signal R of t and convert it to its vector representation R1, R2, and up to Rn in the n-dimensional space. And then the job of the detector is to make a decision as to which could be the possible transmitted signals by observing the received signal vector. Okay, so we have been talking about that in the last lecture, and our focus in the last lecture has been on the demodulator, where we discussed about the correlation type of demodulator. Okay, let us quickly recap the manner in which the correlation demodulator works. So basically, if you look at this diagram here, this depicts the functionality or the operation of the correlation demodulator, where we have n parallel branches of correlators which find the correlation between the received signal and the basis functions, and the correlation equation is given by this, right? So basically, the each arm of the correlation demodulator is computing the projection of the received signal onto one of the basis functions. So the first arm is computing the projection of the received signal R of t onto the basis function phi1 of t. Similarly, the second branch is computing the projection of R of t onto the basis function phi2 of t, and we call those projections as R1, R2, R3 up to Rn. So basically, the demodulator, what it is doing, it is converting the signal waveform R of t into the vector R with the elements R1, R2 up to Rn. So the job of the demodulator is to translate or convert the waveform into its vector representation. So as you see here, R of t is converted to its vector representation, right? And that's the job of the demodulator. And we've done this using the correlation demodulator, and we've seen the analysis for the correlation demodulator in the previous session. But what is the disadvantage of the correlation demodulator? The disadvantage is that the correlation demodulator requires these multipliers. These are analog multipliers which have to multiply the waveforms with the basis functions. So this is the disadvantage of the correlation demodulator, that it requires analog multipliers. So the disadvantage is that it requires analog multipliers, and analog multipliers are difficult to build, okay, difficult to design and build, and the implementation is difficult, not impossible, but because of that difficulty, we want to work out an alternative mechanism of doing the same process. We want to go from R of t to these vector elements or projections r1, r2 up to rn, but we want to do it without the use of these multipliers. Okay, so that's the alternative design that we are going to discuss today, because the presence of these multipliers becomes a disadvantage for the correlation demodulator. So we are going to see today how we can do the same process of converting the signal waveform into the vector representation without using these multipliers. Okay, and for that we are going to investigate or discuss today what is called as a matched filter demodulator. Now, in the matched filter demodulator, the conversion from the waveform to the vector representation is done using n parallel branches, but the branches, instead of having the cross correlators, we have them as linear filters. So each branch of the matched filter demodulator is having a linear filter with a certain impulse response. Okay, so the impulse response is given here, and the whole idea about this is to choose the impulse response appropriately, which makes the matched filter very interesting and very advantageous. Okay, so that's the difference between the matched filter and the correlation demodulator. In the correlation demodulator, we had the correlators, which involved a multiplication and followed by an integration stage. Here we have a linear filter with a certain impulse response. So because we want to convert the signal into a vector of length n, so we have n parallel linear filters which do the process of or which achieve the same functionality as the correlation demodulator, in the sense that each of these branches computes the projection of the received signal onto the basis function phi1 of t, phi2 of t, and so on. Now these are the impulse responses of the linear filters which are used in each of these branches. So phi1 of capital T minus small t, right, and phi2 of capital T minus small t, these are all denoting the impulse responses of the linear filters which are used in each of these branches. So these are basically the impulse responses as we have mentioned here. Okay, now the choice of the impulse responses is what makes the match filter of such importance. Okay, so we will see now how to choose the impulse response for these filters, and then we will also talk about what are the advantages of doing so. Okay, now for a matched filter, as the name suggests, matched filter, the impulse response is matched to the signal of interest, to the signal that we are trying to receive. So in this case, the signal that we are trying to receive is the transmitted signal, which we will call as S of t, and the matched filter's impulse response is matched to the transmitted signal S of t. Right? So what do we mean by that? The impulse response being matched to a given signal S of t means that we choose the impulse response to be a time reversed and causal representation of the transmitted signal or the signal of interest with which we want to match the impulse response. So for example, if we have this particular signal here, S of t, which is of duration t, and it is like a triangular pulse of duration t with the peak amplitude of a volt. Now we have to match the impulse response to this pulse. By matching, we mean to set the impulse response to be a time reversed and causal representation of this signal. So what do we mean by time reversed first? Time reversed means rotating this time axis to the other side, right? So when you rotate the time axis to the other side, so the time axis goes there, that makes it s of minus t. So rotate the time axis about the amplitude axis, so you get s of minus t, which will be like a mirror image of s of t. So you have s of minus t denoted by this, and we can't have this as our impulse response. If we choose, or if we set the impulse response to be equal to s of minus t, then what you notice is that there is an impulse, that there is a response before time 0. So that means the system is non-causal. So we can't have a filter whose impulse response is given as s of minus t, right? Because it is non-causal. What do we mean by non-causal? Non-causal means there is a response or output before time t equal to 0. Okay, that means for t less than 0, for time less than 0, there is some output. So we can't have this as our h of t. Okay, so to make it causal, what we do, we want to shift this to the right by how much? By t, because when we shift it to the right by t, we'll have this entire portion starting from 0. So there won't be any response before time t equal to 0, or for t less than 0 it would be 0. So that would make the impulse response causal. So we want to shift this to the right by a certain amount t. So we have s of minus t done here, and then shift to the right by t. Normally, if you remember, shift to the right means you put by any amount of you would put it as minus t, right? But in this case, because the time axis is already reversed, a shift to the right would become would be a shift by plus t. Okay, a shift to the right by t would be plus t, because the time axis is reversed now. Okay, under the normal conditions, a shift to the right would be a shift by minus t, but because the time axis is reversed, a shift to the right, okay, shift to the right is a shift by plus t. So putting all this together, so we have the impulse response is to be equal to h of t is s of minus t, and shifted to the right by t, which is minus t plus t. So we write this as s of capital T minus small t. So that becomes our impulse response, which is matched to the signal of interest. So our signal of interest is s of t, and we have now created an impulse response for a filter such that that impulse response is matched to the signal s of t. Okay, so the matched filter impulse response looks like this. So this is basically the right shifted version of s of minus t, where it has been shifted by capital T. Okay, so we now know how to create the impulse response, or how to compute the impulse response of a matched filter matched to some signal s of t. Now in our case here, for our implementation, we are interested in matching the signal, matching our impulse response with the basis functions, right? So it is slightly different, because if you notice from the diagram here, we are interested in computing the projections onto the basis functions. Okay, so there will be a slight difference in the sense that rather than matching it to the signals, we will be matching it to the basis functions. So we will match the impulse response of the signal, impulse response of the filter, to the basis functions that represent our signals. Okay, because the basis functions are used to represent our signals. Okay, now given the impulse response h of t of a matched filter, what is the output of the filter? The output is given as the convolution between the input and its impulse response. So the convolution operation is given by this equation. So if the input signal is s of t and the impulse response is h of t, then we have the output to be given as, we use the variable tau here. So the impulse response, or the output, is given by this equation, which is integral s of tau h of t minus tau d tau. Now h of t, if you see in the previous page, h of t is s of capital T minus small t, and so therefore h of t minus tau will be s of capital T minus t minus tau. So minus t minus tau with the minus in front will become t minus t plus tau, right, which is what we have written here. So the output of the matched filter is given by this for an impulse response h of t, which is matched to the transmitted signal s of t. Now if you look at this equation, it is basically like a correlation between s of tau and some shifted version of s of t, right, s of tau. So s of tau shifted by t minus t, right. So it is basically an autocorrelation function, and if you compute this at a certain time capital T, that means if you sample the output of the matched filter at a time capital T, if you sample the value of the output at t is equal to capital T, okay, at t equal to capital T, what happens when you make this t to be equal to capital T? Then t minus t, this disappears, so you have s of tau into s of tau. So at the sampling instant capital T, you get the energy of the signal, okay. So the autocorrelation is going to be maximum at this moment because you're computing the correlation with zero shift. So when you make t equal to capital T, you have s of tau into s of tau. So it's a correlation of the signal with itself without any shift, right? So perfectly aligned signals. So the correlation is going to be maximum at this point. And as you know from the properties of the autocorrelation function, that the autocorrelation function is an even function and it has a maximum value at a shift of 0, which is this case, and that maximum value turns out to be the energy of the signal, which is integral s square of tau, right? So basically we have the peak value here, which is the output of the matched filter at the sampling instant capital T. So at the sampling instant capital T, that peak value is equal to the energy of the signal. Right. And as I said, for our purposes, we are interested in matching the impulse response of the matched filter to the basis functions that are used to represent our signals. So the basis functions that we have are phi 1, phi 2, phi 3, and so on up to n, up to phi n, which is n basis functions. So we want the n linear filters to be matched to each of these basis functions. So the filter in the first branch of our matched filter demodulator is matched to the first basis function. So if the first basis function is phi 1 of t, we have the time reversed version phi 1 of minus t, and to make it causal we shift it by capital T to the right, so phi 1 of minus t plus t, so we get phi 1 of capital T minus t. So that's our first impulse response for the linear filter in the first branch of the receiver. Similarly, we have the impulse response of the second branch filter to be matched to the second basis function, and so on. So we have, in general, for each of these n branches, we have the corresponding impulse response matched to a corresponding basis function. Okay, so the outputs of these filters, we want to have them to be as the projections of the signal r of t onto the basis functions. So what would be the output of the filters? It will be the convolution of this signal r of t with the corresponding impulse response. So let us see what happens when we compute the convolution between the signal and the basis function. So the output is simply going to be the convolution between the signal, the input signal R of t, which is basically the received signal, and the corresponding impulse response in that branch. So y1 of t would be R of t convolved with h1 of t, and so on. So when we compute this, we get R of tau into h of t minus tau d tau. Now the impulse response is matched to the corresponding basis function. So hj of t is given by this. So the shifted version of the impulse response now will become phi j of t minus tau. So you can see this diagram, this particular calculation here, to see how we get the shifted version of the impulse response to be equal to the shifted version of the corresponding basis function. So now we have the output of the matched filter to be in each of those branches j, for j1 to n, to be given by this equation. And then again we are going to sample this output at the time t is equal to capital T. So when you make the small t equal to capital T, that means at this small t equal to capital T, this term disappears, so you get R of tau into phi j of tau. So at the sampling instant t equal to capital T, you get the output of the matched filter to be equal to the projection of the received signal onto the basis function. So if you recall the expression for computing the projection of any signal, it is the signal, the integral of the signal multiplied by the corresponding basis function, right? So which is nothing but the corresponding projection. So when we have what we have in the first branch, y1 at the sampling instant capital T is the projection r1, y2 of capital T is the projection r2, and so on. So we end up with computing these projections r1, r2 by taking the output of the corresponding matched filter and sampling it at the time t equal to capital T. So when we sample it at that time, we get the corresponding projections. And by the way, at that time t equal to capital T, the value is maximum, right? So let us see now. So what happens is, by doing this procedure, we are now able to convert the signal R of t into its vector representation by computing the vector elements r1, r2, r3 up to rn, and we have done so without using any analog multipliers. Okay, we have implemented this using a matched filter demodulator, wherein the impulse response of the matched filter is matched to the signal of interest. In this case, it is matched to the basis functions of the signal space that represent our signals. So by doing so and sampling at a specific moment, we are able to compute the projections of the received signal R of t onto each of the basis functions. So we have done this implementation now using linear filters rather than using analog multipliers. So we have got rid of the analog multipliers, and we have done the same process as we did in the correlation demodulator, but without the use of analog modulators. So the matched filter implements the demodulator part, which converts the signal, the received signal R of t, into its vector representation R with the elements R1, R2, R3 and so on, by using linear filters with impulse responses matched to the basis functions. So we have the linear filters whose impulse responses are matched to the basis functions. Okay, so we have achieved the same results without using analog multipliers in this case. Okay. Now let us look at some properties of the matched filter. But before we go into the properties of the matched filter itself, I want to reiterate that the properties of the received signal vector, okay, and in particular the statistical properties, they remain the same as in the case of the correlation receiver. If you recall in our last session where we discussed about the statistical properties of the correlation receiver's output, which is what is the probability distribution of R1, R2 and so on, and then the probability distribution of the vector R itself, right? So you notice that it had a Gaussian distribution which had the variance or standard deviation to be the same as the noise standard deviation, and the mean value was equal to the mean of the transmitted signal. So the noise mean is 0, the transmitted signal has some mean SM1, SM2 and so on, so the mean value of the received signal is the same as the mean value of the transmitted signal, but the standard deviation remains unchanged, right? And with that we had some expression which was a Gaussian distribution with a certain mean and certain standard deviation. Okay, so those statistics, those properties remain the same, even in the matched filter demodulator. So you can look back at the analysis we did in the correlator demodulator to find those properties, the statistical properties of the received vector and the received vector's elements, right? So those remain unchanged. Okay, but let us now focus on some properties of the matched filter itself. Okay, and one of the important properties of the matched filter is that when you have the impulse response of the receiver filter matched to the signal of interest, then the output of the matched filter produces the maximum signal to noise ratio. That means the matched filter output maximizes the SNR of the output of the filter. So by having a matched filter, the SNR at the output of the matched filter is maximum. Okay, so we are going to prove this point, and we are going to start with a general case, and then we'll show that the SNR indeed gets maximized by having the impulse response to be matched to the signal of interest. Okay, so let us quickly break down our receiver or the matched filter output into the signal component and the noise component. So the output of the matched filter is the convolution between its input and its impulse response. The input to the matched filter is nothing but the received signal, which is R of t, and the impulse response of the matched filter is H of t. So the output of the matched filter would be given by the convolution between the input signal and the impulse response. So you have this convolution equation here. But we know that the received signal R of t is the sum of the transmitted signal and the noise signal. So we put that there. R of t is the S of t plus N of t. Of course, the variable used here is tau. And then we break this integral into two parts. So we have the output of the matched filter containing the signal component, which is the convolution of the transmitted signal with the impulse response of the filter, plus the convolution of the noise signal with the impulse response of the matched filter. So we call this part to be the signal component of the matched filter output, and this part to be the noise component of the matched filter output. So, and we represent that as okay, so we'll call the signal component as ys of t. So the signal component of the output y of t is ys of t, and the noise component is yn of t. And again, if you notice here, we are sampling it at the moment of interest, which is capital T, at the time t equal to capital T. Okay, if you put t equal to capital T, which is our moment of interest, we get the output at the sampling instant, which we will call as the signal component at the sampling instant, and the noise component yn of capital T at the as the noise component at the sampling instant capital T. So we have the output of the match filter divided into two components, the signal component and the noise component. Now we are interested in the signal to noise ratio. We stated earlier that that one of the properties of the match filter is that it maximizes the signal to noise ratio, right? So that means when we have this impulse response to be matched to the signal S of t, then the signal to noise ratio, that means the signal power or the power in the signal component to the ratio of the power in the signal component to the power in the noise component would be maximum, right? And that is what we are interested in. We want to have the signal to noise ratio as high as possible, and match filter as an inherent property indeed maximizes the signal to noise ratio at the at its output. Okay, and that is what we are going to prove now. So what is the signal component? Of course, the signal is a deterministic part. Okay, the transmitted signal that we have is a deterministic signal, so the signal power would simply be the square of the signal's amplitude. So if we have the signal component as ys of t, its power is simply ys square of t, so which is the square of the first integral, right? So this entire integral, which is denoted by as the signal component, so the signal power is the square of this entire integral. Okay, we'll keep it aside for now and we will come back to it later to simplify this. Okay, as of now we'll just keep it as the square of this integral to represent the signal power, which we denote as the letter capital S. Okay, what about the noise power? We can't say the noise power is simply yn square of t as the signal power, because unlike the signal component, which is a deterministic component, the noise is not deterministic. Noise is random. Okay, so because the noise is random, we need to use the statistical methods to find the noise power, and therefore the noise power, given that the noise we are dealing with is zero mean, so the noise power is given by the variance. So we need to compute the variance of the noise component, which is given as the expected value of yn square of t. So that's the definition for variance, right? The expected value of yn square of t. So that would be the noise component, the noise power. So yn square of t, we are going to substitute this second integral here that we have in place of yn of t. So yn square is going to be this integral multiplied with itself. So the expected value of this integral into itself, right? So let's substitute that. So we have the noise power to be given as the expected value of yn of t into yn of t, and because we are multiplying the integral twice, we just separate the variables. Here we denote the variable as tau, and here we denote it as t. Okay, otherwise they are basically representing the same yn of t, right? So now we just simplify this equation a little bit. We just rearrange the terms and interchange the expectation and integrals. Okay, reorder the expectation and integration operators, and we begin to get some insight into what this is actually representing. So we take the integrals outside and we combine n of tau and n of t and put the expectation for n of tau into n of t into, we have this h of t minus tau, h of t minus t, d tau, dt, all of them are there, right? Now if you look at this particular part of this equation, we have expectation of n of tau into n of t. This is basically representing the correlation between n of tau and n of t, or it's the autocorrelation function, for the noise process, right? And as we know that the noise process is uncorrelated, that means this product will have a non-zero value only when t is equal to tau. So that's the nature of white noise, right? White noise is uncorrelated. That means the autocorrelation is non-zero only for zero shift. So only when t1 and t2, which in this case is tau and t, are equal. So for t not equal to tau, if these two parameters or arguments are not equal, then this entire term becomes zero, right? So it is non-zero only for t equal to tau. So and that non-zero value, if you recall right on the first page of this lecture, the autocorrelation function is given as n naught by 2 delta of tau. In this case, for t equal to tau, it is n naught by 2 delta of t minus tau. So that becomes the autocorrelation given by this equation. So we are going to substitute this in place of the expectation operator here, and we get the noise power to be given by this. So in place of E of n of tau into n of t, we have this n naught by 2 delta of t minus tau, and because n naught by 2 is just a number, we take it outside the integral, and we invoke the fact that the delta function, this is a shifted delta at t equal to tau, so that means this entire integral would be non-zero or only when t is equal to tau, right? So for all other values of tau, this integral will evaluate to 0. So when you make small t to be equal to tau, that is delta of 0, that will be 1, and small t and tau are now equal. Okay, so we'll put t minus t and t minus small t. So the tau and t become the same now. So we have n naught by 2. This delta term is equal to 1 for t equal to tau. And then we have inside the integral h of t minus t. So because tau is t, and h of t minus t as it is, right? And dt. So basically we can split this now into the two integrals. And basically you get this as n naught by 2, the square of the shifted version of the impulse response h squared, right? So the noise power is now given in terms of the noise power spectral density n naught by 2, and the if you look at this equation, it is nothing but the energy of the impulse response, right? If you have the impulse response h of t, this integral h square of t is nothing but the energy of the impulse response. So we see that the noise power depends on the power spectral density of the noise process and the energy of the impulse response. So now let's put things together. So we first computed the power of the signal component, right? So we had the signal component ys of t, and its power is ys square of t because it's deterministic, which is given by the square of this integral. And then we computed the power in the noise component at the matched filter output, and the power in the noise component we have found out to be, that it is represented by this expression here. Okay, n naught by 2 h square of t minus t, which is basically saying that the noise power at the output of the matched filter depends on the noise power spectral density and the energy of the impulse response. Okay, so that is what is I have stated here. So the noise power depends on the power spectral density and the energy of the impulse response. Okay, right. Now we are interested in the signal to noise ratio. So we have the signal power given by the square of this integral which is ys square of t, and we have the noise power given by the previous equation we just saw in the last page, right? So this is our noise power, and this is our signal power. So we want to find the ratio of the signal power to the noise power. So in place of the signal power, we substitute this integral, and in place of the noise power we substitute this expression. So we get the signal to noise ratio at the output of the matched filter, so which is given by this. Now the objective is to maximize this ratio. We want to have the signal to noise ratio to be maximized. And how do we maximize this? Again, so far we have not specified what should be the impulse response here. We just say it's an impulse response. So what we are going to show now is that by choosing the impulse response to be matched to the transmitted signal S of t, we will see that this ratio indeed gets maximized, and for that we are going to utilize some properties like the Cauchy-Schwarz inequality, and also invoke the Parseval's relationship. Okay, so let us see how we can prove this. Okay, now to maximize this ratio, one of the things we can do is we can consider that the denominator to be fixed, and for a fixed denominator maximize the numerator. Okay, so we want the numerator to be as high as possible. If you want to maximize this ratio, make the signal power large and make the noise power small. That will increase it. But to approach the problem, we are going to say, okay, n0 by 2 is fixed. This is the energy of the impulse. Let's say this is fixed as well. And when the denominator is fixed, we want to maximize the numerator. And in the numerator, you have the transmitted signal, which is what you want to transmit. So the only thing you can play with to maximize this is the impulse response h of t. So we need to choose h of t in an appropriate way such that the numerator term gets maximized, and that is going to be our objective. So we want to maximize the signal to noise ratio by choosing the appropriate function for the impulse response, by choosing an appropriate impulse response and considering that the denominator is fixed, it's not changing. We will show that by choosing the impulse response to be matched to the signal S of t, the numerator gets maximized, and hence the signal to noise ratio gets maximized. And we will show that when it is matched to S of t, that is what we call as matched filter, and that is when we get the maximum value for the signal power for a given noise power. Okay, that means the signal to noise ratio is maximized for the matched filter at the output of the matched filter. Okay, so let us look at the signal power part. So we are going to focus on the numerator part. So now this is a square of the integral, and the integral has two components, right? S of tau and h of t minus tau. And if you recall from our lecture 3 where we did the Cauchy-Schwarz inequality, where we had where we show that the square of an integral which has the product of two functions within the integral, okay, so that is less than or equal to the squares of the functions integrated separately, right, and multiplied together. So this is this equation here denotes the Cauchy-Schwarz inequality. That means this integral is always going to be less than or equal to the functions squared and integrated separately, right? The product of the functions squared and integrated separately. So when we have when we invoke this Cauchy-Schwarz inequality, and we will see that when does this equality satisfy? The left side is always going to be less than the right side. It will be equal to the right side only under one condition. And what is that condition? The condition is that g1 of t and g2 of t should have an angle of 0 between them, right? That means the two functions g1 and g2 should be in the same direction or they must be proportional signals. That means their vector representation should lie on the same line. That if the vector representations of g1 of t and g2 of t lie on the same line, that means the angle between them is 0, and that means when the angle between them is 0, that means one signal is a scaled version of the other signal. So we can have g2 of t is some scaled version of g1 of t, or g1 of t as some scaled version of g2 of t. Either way, we just say that these two signals are proportional signals, and when the two signals are proportional to each other by some proportionality factor which we call as c, that means the angle between them is 0. That means they are along the same line in the signal space. In this case, the equality is achieved between the left hand side and the right hand side of this inequality. So that equality is the maximum value that this left hand side can have, right? So the equality is achieved when the signals are in the same direction, that is they are proportional to each other. Okay, so we have in our case s of tau as our g1 of t and h of t minus tau as our g2 of t. So we will treat these as two signals g1 and g2, and then show that by having g2 as some signal proportional to g1, that means by having h of t to be proportional to s of t, we can achieve the equality in the Cauchy-Schwarz inequality representation, right? So that way the numerator would get maximized, and for a fixed denominator we can say that the signal to noise ratio gets maximized. So let me highlight what I want to say here. So by setting g2 of t as our h of t minus tau in our equation, and g1 of t as the signal itself, we are going to see how we can maximize the signal to noise ratio by achieving the equality in the Cauchy-Schwarz inequality. So let's see that in more detail. So when we choose our impulse response h of t to be the signal matched to the signal s of t, which is the time reversed and shifted version of the signal with some proportionality factor or scaling factor c, and then we substitute for g1 of t and g2 of t. So g1 of t is s of t, g2 of t is h of t minus t. So because we chose the impulse response to be matched to the signal s of t, so h of t minus t simply becomes c times s of t, right? So we're just going to substitute these in our equations. So in place of s of t, which is our g1 of t, we have this. In place of g2 of t, which is h of t minus t, we have c times s of t. So substitute that, and under that condition, because we have chosen g2 to be some scaled version of g1, the equality holds. So the inequality in the Cauchy-Schwarz is now an equal sign here, because we have chosen g2 of t to be proportional to g1 of t. So we have the equality here, and now we clearly see that it is s square of t. That's the energy of the signal, and that's also the energy of the signal, and that's the proportionality factor c that has been squared now. Okay, so now we substitute this in the signal to noise ratio equation. So we'll substitute h of t to be given by this. So our signal to noise ratio equation, we go back to that. So we have this this integral squared, and because now we have chosen g2 of t to be proportional to g1 of t, we get this maximum value for the numerator, which is given by these two by the product of these two integrals. So we have these two here in the numerator, and that is the maximum value, so hence we say this is equal to. And the denominator part, we had n naught by 2 into the energy of the impulse response. Again, this h square t minus t is going to be c square s square of t, right? So we just substitute in place of h of t minus t. So in the denominator also we represent the impulse response in terms of the signal, because we have chosen the impulse response to be matched to the signal s of t. So the shifted version of the impulse response gives us s square of t, right? So now these calculations are shown here, okay? So when we substitute all the terms, what we see is that we get the signal to noise ratio, which is the maximum value that we can have, because we have now maximized the numerator by choosing g2 of t to be proportional to s of t. How it is proportional? G2 of t, which is our impulse response, it is some scale version of the transmitted signal, but it is also shifted and time reversed. Okay, that doesn't change the value, but it is just the direction and the shift which has been changed. So it is still proportionate to the signal s of t. So we get the maximum signal to noise ratio. So this s square of t integral and s square of t integral, c square and c square, these are all cancelled. So we are left only with this term, right? So that integral there denotes the energy of the transmitted signal, which we denote by Es, and the n naught by 2 in the denominator, we can bring the 2 to the numerator. So we have the signal to noise ratio given by 2 times Es by n naught. Okay, so what we see here is that the maximum signal to noise ratio at the output of the linear filter is achieved when the impulse response of the linear filter is matched to the signal of interest s of t. So by choosing the impulse response h of t to be a time reversed and shifted version or causal representation of the transmitted signal, and we have used a scaling factor also here, we are able to maximize the signal to noise ratio, and that maximum value of the signal to noise ratio is given by this expression. So the maximum signal to noise ratio is 2 Es by n naught, and this maximum is achieved by matching the impulse response to the transmitted signal s of t, right? So we have matched the impulse response of the linear filter to the transmitted signal s of t, and by doing so we have achieved this maximum signal to noise ratio. All right, okay, to summarize, we see that by using the matched filter whose impulse response is matched to the transmitted signal, we are able to maximize the signal to noise ratio of the output of the filter. That means the output of the matched filter produces the maximum signal to noise ratio. All right, and the other interesting thing that we notice here is that the output signal to noise ratio, as seen from this equation here, the maximum signal to noise ratio, it depends on the energy of the transmitted signal, but it does not really bother about about the other aspects of the transmitted signal. All it depends is on the energy of the transmitted signal Es. Okay, it does not depend on other characteristics like the shape of the signal or the form of the signal or its spectral characteristics, right? You can have a rectangular signal with the energy Es, or you can have some other shape of the signal with the same energy Es. It wouldn't matter. The output of the matched filter would still have the same signal to noise ratio. Okay, so that's another interesting property of the matched filter, that the signal to noise ratio at its output depends on the energy of the signal that we transmit, but it does not depend, or it's oblivious to the other aspects of the transmitted signal. Okay, the other characteristics of the transmitted signal. Okay, I'll stop here for now, and in the next lecture we will discuss about the match filter in the frequency domain. So we look at some properties of the match filter in the frequency domain or in the spectral domain, and we will come to the same conclusions, but we will analyze it in the frequency domain. Okay guys, thank you.